Hi everyone and welcome back to the Mass Material channel. In our previous video, we learned about different theorems and rules such as the Sandwich theorem, the continuous function theorem, and the L'Hopital's rule for calculating limits of various sequences. If you missed the lecture, no problem. You can watch it in the playlist link below. Today, we are gonna learn how to calculate some frequently arising limits. It's a good idea to memorize these limits because they will help us in future videos when we start learning about infinite series. Okay, let's say that we have this sequence which is defined by a sub n is equal to natural log of n over n. For calculating the limit for this sequence, we can write the limit as n approaches infinity of natural log of n over n, which is equal to infinity over infinity. We have learned from our previous video that whenever we have infinity over infinity or 0 divided by 0, we can use L'Hopital rule for calculating the limit. So we know that we can take the derivative of both the numerator and the denominator for calculating this limit. The numerator for the the derivative for the numerator for natural log is just 1 over n, and the derivative for the denominator or n is simply 1. So we have the limit as n approaches infinity of 1 over n, and we know that this limit is equal to 0. So since the limit is equal to 0 and it's a specific value, we can claim that this sequence is convergence. As another example, let's find the limit for this sequence, which is defined by a sub n equal to nth root of n. For finding the limit for this sequence as n approaches infinity, we can use the fact that the limit as n approaches infinity of natural log n over n is equal 0. We find the limit for this sequence in our previous example. So how can we use this expression to find the limit of this sequence? Let's define x equal to the nth root of n. Then we have x to the power of n equals to n. If we take the natural log from both sides, we can write the expression that n times natural log x equals to natural log n. Then the natural log x is equal to natural log n over n. If we take the limit from both sides of this expression as n approaches infinity, we can write that the limit as n approach infinity of ln x equal the limit of natural log n over n. Based on our previous example, we know that the limit for this sequence is equal to 0. So we can conclude that the limit for ln x as n approaches infinity is also 0. In our previous video, we have learned that the limit passes through the continuous function. So based on the continuous function theorem, we can rewrite the expression like this. The ln of the limit as n approaches infinity x is equal to 0. And based on the log rule, we know that the limit as n approaches infinity of x is equal e to the power of 0, which is equal to 1. If we substitute the x with the nth root of n, the result is the limit as n approaches infinity of nth root of n is equals to 1. In our previous example, we proved that the limit as n approaches infinity for the n raised to 1 over n is equal to 1. Based on this calculation, we can also conclude the limit as n approaches infinity for any positive number raised to 1 over n is also equal to 1. Now let's prove this expression. We can define the a to the power of 1 over n with a new variable like y. We can rewrite this expression like y to the power of n equals to a. If we take the natural log from both sides, n times ln y is equals ln a, and we can write that ln y is equal to ln a divided by n. If we take the limit as n approaches infinity from the both sides, ln y is equals to the limit as n approaches infinity of ln a divided by n, and we know that this is a constant and the limit of 1 over n as n approaches infinity is equal to 0. So we can conclude that the limit as n approaches infinity of ln y is also equal to 0. Based on the natural log rule, we can conclude that the limit as n approaches infinity of y is equal to e to the power of 0, which is 1. So we prove that for any positive number, the limit as n approaches infinity of a to the power of 1 over n is equal to 1. Now let's try another example and find the limit for this sequence a sub n equals to 1 plus x over n raised to the n. In order to find the limit as n approaches infinity for this sequence, first of all, we can take the natural log from both sides. So the ln a sub n equal to n times ln 1 plus x over n. So the reason for taking the natural log from both sides is to taking the n and putting them in the front. So by using the L'Hopital rule, now we can calculate the limit. But here, as n approaches infinity, we have infinity times 0, because as n approaches infinity, this part tends to infinity and this part tends to 0. For using the L'Hopital rule, we know that we should change or convert the limit in order to reach to the infinity over infinity or 0 divided by 0. To do this, we can simply substitute the n with 1 divided by 1 over n. So our expression is now the ln of limit as n approaches infinity of a sub n is equal to the limit as n approaches infinity of ln 1 plus x over n divided by 1 over n. We simply substitute the n with 1 divided by 1 over n. Now we can now use the L'Hopital rule by differentiating the denominator and the numerator. We know that the derivative for the function ln u is u prime divided by u. Here in this example, u is equal to 1 plus x over n. If we take the derivative from u, it's gonna be 0 minus x divided by n squared. So if we take the derivative from both the top and the bottom, we have the derivative of the numerator u prime divided by u, which is minus x over n squared divided by u, which is 1 plus x over n, and the derivative of the bottom is minus 1 divided by n squared. We know that these two terms cancel out each other, and the negative 1 cancel this negative. Then we have the limit as n approaches infinity of x divided by 1 plus x over n. As n approaches infinity, we know that these parts gonna be 0, so the limit is gonna be x. So our final answer is ln of limit as n approaches infinity of a sub n is equal to x, and since in the natural log the base is a, we can conclude that the limit as n approaches infinity of a sub n equal to e to the power of x. So we found that the answer for this limit is e to the power of x.